Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In today's lecture, we will discuss the solution of hydrogen atoms quantum mechanical problem that we derived in our last few lectures. We have come to a place where we have discussed the Schrodinger equation corresponding to hydrogen atom, and we have also obtained an analytical expression for the energy levels of hydrogen atom. We will continue our discussion from there. If you remember, we obtained the expression for the energy level as E n given by minus a square divided by 2 mu a square z square divided by n square, where a is the constant known as the Bohr's radius, whose value is 0.529 angstrom, and h bar and mu are again constant for the system. H bar is the universal constant and mu is the mass of electron or the reduced mass of the hydrogen atom. So, together this quantity is also a constant and its value is its value is 13.6 electron volt multiplied by we have z square by n square, and this expression is now given in electron volt unit, because we have used the values of this constant and converted this quantity to electron volt unit, and this value is minus 13.6. Where you see this other term z square, z is the nuclear charge of the system and n is the new quantum number whose value turned out to be 1, 2, 3, so on so forth. The lowest possible value was of n is 1. We discussed why n equals 0 is not allowed in our last lecture. So, suppose now I put n equals 1. Before that, let us say I am considering hydrogen atom. So, therefore, z is equal to 1, and while I am considering hydrogen atom, so therefore, z is 1. When I put n equals 1, this energy level E 1 would turn out to be simply minus 13.6 electron volt. Similarly, if I use n equals 2, the second energy level I would get as minus 13.6 divided by 4. I am getting 4 because n square, n is 2, so n square is 4, and this would turn out to be something around 3.4 electron volt. And similarly, when you do n equals 3, you would see E 3 would turn out to be about 1.51 electron volt. Please note that all these numbers are in negative, because we have this negative sign over here. Similarly, you can continue with higher and higher values of n and you would see the energy. If I have to plot this energy level, so this is my energy axis. So, E 1 turned out to be minus 13.6 electron volt, E 2 minus 3.4 electron volt, E 3 is minus 1.51 electron volt. And if I continue to do this, you would see that the next one will be something around minus 0.85 electron volt, and so on and so forth. One thing that you must have realized now is that the energy spacing between two consecutive levels keep on decreasing as we go higher in energy. So, this is n is 1, 2, n is 3, and so on. So, as we increase n, of course, the energy is increasing, but the spacing between two consecutive energy levels are decreasing. Now, you imagine the case where n is very large, or to the limit n goes to infinite. When n goes to infinite, then you see that we have this energy expression 1 over n square term. So, this quantity will become, where n is very large quantity, this energy becomes 0. All other energy levels where n has any finite value, you would see that the energy will be negative, and when n goes to infinite, this will become 0. But as we see that when we go higher and higher in energy level, the spacing between two consecutive energy level would decrease. So, you can imagine at when I go to sufficiently large value of n, I would not see any discrete energy levels, but rather the spacing between them will be so less that it will be practically a continuum level of a continuum set of energy levels. So, this happens when n is very large. For smaller values of n, the energy levels are discrete or quantized. At higher values of n, the energy levels start appearing so close to each other that as if they form a near continuum. And this would terminate until even when n goes to very large value, this would terminate when energy is. So, if I continue this my energy axis, so this is my energy 0 axis. So, all these energy levels will terminate when energy is 0. That is because when n goes to infinite, the energy is 0. So, all the states of hydrogen atom have negative energy. The negative value of this energy is manifestation of the fact that there is an effective attraction between the electron and the nucleus. This attractive force contributes to the negative sign of the energy levels. But if you, and all these energy levels are called the bound states. They are bound states in the sense that the electron is still quote unquote bound to the nuclear environment or to the nucleus. Electron still experiences the nuclear field. That represents the bound state. When energy is positive, that would represent that the electron has left the nuclear environment and it is a free particle or it is unbound. If you remember in the course of our discussion for the energy levels, at one point we decided to consider only the negative value of energy, and we said that for positive values of energy, the state of the electron is unbound. That means, it is a free electron and it is no longer a hydrogen atom, rather it has come to a situation that the electron is completely free of the nucleus. So, we have a plus charge, nuclear charge with plus sign, plus charge and a free electron. So, this system, this hydrogen atom would said to have been completely ionized, and then I am left with an electron and a proton. But we are in the quantum mechanical analysis that we are carrying out, we are mostly concerned about the bound states of this hydrogen atom problem, and we have seen these energy levels. All these things we discussed, the energy levels we wrote down were for z equals 1. Suppose I consider z equal 2. Z equals 2, that means nuclear charge is 2. Which system would have? We would have, for example, the helium atom. So, if I consider helium atom, it would have Z equals 2, on the nuclear charge as plus 2e, but helium atom would also have 2 electrons. The discussion that we had, the Hamiltonian that we wrote down for hydrogen atom, it had only 1 electron. So, the solution that we have obtained is applicable only for that system where there exists only 1 electron, not more than 1 electron, because when we have more than 1 electron, there exists a very important interaction, that is electron repulsion, which unfortunately we have not considered in our problem yet. So, therefore, since we have not considered that electron repulsion term, we cannot extend this solution that we have obtained to any system which has got more than 1 electron. In other words, all the results that we are getting are applicable to a system where there exists 1 electron which is going around in the central field of a nucleus of Z charge. So, in this case, if I have to use this or apply this knowledge of hydrogen atom to some form of helium, is that I have to consider a helium plus. When I have helium plus, I have removed 1 electron from helium. So, therefore, Z is 2, but number of electron is 1. So, therefore, helium plus, or in similar way lithium 2 plus and so on, as long as I have a nuclear charge in the center and 1 electron and only 1 electron goes around the nucleus, I can use this energy level expression that I have. So, for example, for helium plus I would simply use Z as 2 and then the rest of the things would remain same. So, for helium atom the ground state energy will have minus 13.6 multiplied by Z is 2. So, Z is 4 divided by n equals 1. So, 4 times E0 where E0 is 13.6 electron volt. So, this is the ground state energy of helium atom, and for the first excited state or the next energy level of helium atom I will put in place of n square as 1, I will use n square as 4. So, therefore, the second energy level of helium atom will simply become minus 13.6 electron volt. So, this way we can derive energy levels of hydrogen like. So, these are called hydrogen like systems. By that we mean that they have a nuclear charge of some value and one and only one electron is going around the nucleus, just like hydrogen atom. Now, since we have now an idea about the hydrogen atom energy levels, we will now go for to discuss the hydrogen atom's emission spectrum. If you remember, hydrogen atom's emission spectrum was one of those experiments that classical mechanics could not explain, and Bohr with his Bohr's atomic model where he proposed that the electrons should go around fixed orbits and the angular momentum of the electron are quantized. By these two assumptions, Bohr formulated his atomic model, and using that atomic model he could explain the hydrogen atom's emission spectrum. But to remind you, Bohr's atomic model could not explain the hydrogen atom's emission spectrum in the presence of external electric or magnetic field, nor it could describe the emission spectrum of heavier atoms. So, there were two shortcomings of Bohr's atomic model. But now what we have done is that our energy levels that we have obtained are obtained from quantum mechanical arguments. So, therefore, they are going to, we would show that the energy level expressions that we are getting will be also applicable to those systems where Bohr's atomic model failed. But before that, we would look at whether our quantum mechanical solution that we obtain is able to express the hydrogen atom's emission spectrum. To do that, see, we would start with this energy level energy expression, that this is minus 13.6 electron volt Z square divided by n square. This is written in electron volt unit. Suppose I am talking about an emission spectrum from N2 to N1. So, therefore, I would write down as En2 minus En1, that energy difference. This would be simply minus 13.6 Z square. I am keeping Z square, but if I am considering only hydrogen atom, so you know that this Z will become 1. So, its effect will be nothing, but then to make the expression generic for all hydrogen like systems, I am retaining this Z square. So, N2 square. So, this is the energy of N2 level, and if I do this minus N1 level, I simply have N1 square. So, this is the energy difference between the two levels. When I am talking about the emission spectrum, instead of expressing this in electron volt unit, I would be interested in expressing it in terms of a wave number. So, in this case, I would simply divide this expression by hc, h as the Planck's constant, c is the speed of light. And now this is expressed in centimeter inverse unit, the unit of wave numbers. So, when you look at this quantity 13.6 electron volt divided by hc, so this is in electron volt and hc. So, when you do an conversion of unit, you would see the value of this would simply be your Rydberg constant that you already are familiar with. So, if you remember, using this Rydberg's constant, we could describe all the different regions of hydrogen atoms emission spectrum by using N1 as 1 and N2 is anything greater than 1, we would get Lyman series. N1 as 2 and N2 is greater than 2, we would get Balmer series, and so on and so forth. So, all the series Lyman, Balmer, Paschen and so on could be described by a single relation using this Rydberg's constant, and now we see that we are reproducing this Rydberg's constant from the energy levels that we obtain from the quantum mechanical solution of hydrogen atom problem. Again, to remind you, even Bohr's atomic model could also reproduce this. So far we have seen that the Bohr's atomic model and the quantum mechanical formulation of hydrogen atom are still they agree to each other, but we would soon realize that how the exact quantum mechanical formulation of hydrogen atom problem is a step ahead of Bohr's atomic model. So, once we have different values of N1, we can easily obtain nu bar and then we can reproduce the emission spectrum of hydrogen atom without any trouble. Now, since we have discussed the eigenvalues of hydrogen atom problem, now we will discuss some little bit about the eigenfunctions of hydrogen atom. If you remember the eigenfunctions of hydrogen atom problem, we said that let the eigenfunction be psi, which would depend on 3 spherical coordinates r, theta and phi, and we did a variable separation and we said that let this total wave function be a product of a radial function r of r and an angular function y of theta phi. We started our discussion, or we have carried out the solution of hydrogen atoms quantum mechanical solution by taking this variable separation strategy. So, here our total wave function is the product of a radial function and an angular function. To remind you, this angular function turned out to be exactly the same eigenfunction of L square and Lz operator. So, these y functions were the spherical harmonics where if you remember these spherical harmonics depend on 2 different indices L and M, and L value can be either integer or half integer. However, since we are discussing the problem of orbital angular moment of electron, where the electron is orbiting around the nucleus, the only allowed values of angular momentum are integer, but not half integer. So, L is 0, 1, 2 and so on so forth, and if you remember, for each value of L, I have 2L plus 1 number of M values, where the M values go from minus L to plus L in the step of 1. So, minus L to plus L in the step of 1 would give me, so number of M values is 2L plus 1 for a given value of L. So, this we knew about the spherical harmonics. So, what we would do is that we would give this index Lm to this y function or the spherical harmonics. This we knew from angular momentum solution, so therefore, we used it. Now, the radial part of the solution is something that we derived for the first time in case of hydrogen atom problem. If you remember, we defined our radial function r as a function of r as 1 over r into u of rho, where rho was given by k r, and from our previous discussion we saw that k is z over a n. So, rho is z over a n by r, and I have this function u which is defined as in rho. If you remember, we derived the form of u by looking at its asymptotic solution at low value of r, at very high value of r, and the main body of the problem. So, we had this 1 over r rho to the power L plus 1, this is one asymptotic solution, e to the power minus rho, this is the other asymptotic solution, plus the main body of the problem which we called as V of rho, where this V of rho we wrote down. Since we did not know what is the functional form of this, we used a power series expansion for this V of rho, where we defined V of rho be a sum of Bj rho to the power j, where j goes from 0 to some value of j max, where we saw j max. We discussed that this cannot be an infinite series, that would make the wave function unacceptable. So, this series must truncate somewhere, must terminate somewhere, and that j max value turned out to be n minus L minus 1. So, now I can write the j goes from 0 to n minus L minus 1 Bj rho to the power j. So, this is the general form of the radial part of the solution. Now, let us look at what kind of indices does this function depend. Clearly, I see that it has an explicit dependence of rho to the power L plus 1. So, it depends on L. What else does it depend? When I look at this sum of this summation series, I see that it also depends on n, because it is not sufficient if I know only L value, because I have my series will truncate at n minus L minus 1. So, therefore, n is also a quantity on which this function depends. So, the two indices on which the function depends, the radial function depends, are n and L. So, we give this indices n L to this radial function. So, now we have two functions, one radial function, another angular function. Radial function depended on n and L, the angular momentum functions depended on L and m. Now, both the functions have L in common. So, therefore, there exists a continuity between the two. So, if you see, for a given value of L, I have 2L plus 1 number of m values. What are the values of, how are n and L related? You see, the j max, the maximum value of a j is given by n minus L minus 1. So, therefore, the maximum value of j, the minimum value of j is 0, it goes from 0 to j max. So, therefore, the lowest possible value of j max that we can have will be 0, and when I have this one as 0, then you would see that n is equal to L plus 1. This will be the this should be the maximum value of L corresponding to a particular n value. So, in other words, the L values can become 0, 1, 2, so on so forth until n minus 1. So, I see that there are, for a given value of n, I have n number of L values. What are they? They are 0, 1, 2 until n minus 1. So, for a given value of n, I have got n number of L values, and for a given value of L, I have got 2L plus 1 number of m levels. So, to find out overall total degeneracy of the system, we would see that for a given value of L, we have 2L plus 1 number of m levels, and how many such n levels are there? How many such L levels are there? There are n number of L levels. So, here L goes from 1 to n. So, if you see, so for a given value of n, I have n minus 1 number of L values, sorry n number of L values starting from 0 till n minus 1. since there is a 0. So, therefore, the total number of L values are n. So, therefore, my sum is now L goes from 1 to n, and for each value of L I have 2L plus 1 number of m values. So, the total number of eigenfunctions for a given value of n can be obtained from this expression. If I do this, I have now two terms over here. The first term L equals 1 to n plus, when I look at the second term, this is plus 1. How many times? It is n times plus 1. And when I do this sum, L goes from 1 to n, we know that this value is n into n minus 1 divided by 2 and plus. So, I get n square minus n plus n, this is n square. So, this tells me that for a given value of n, I have n square number of eigenfunctions. What about the energies? The energy, on the other hand, depended only on one level, that is only on one index, that is n, whereas while energy E n depended only on n, for a given value of n, I can now have n square number of eigenfunctions. So, therefore, the hydrogen atom's energy levels that we drew in an earlier slide, E1, E2, E3, E4 and so on, the degeneracy, the level of degeneracy of these energy levels are given by n square. So, for E1 I have n square is 1. So, there is one function which has energy of E1, which is minus 13.6 electron volt. For E2 I will have 4 different eigenfunctions which will have the energy of minus 3.4 electron volt, and equals 3 I should have 9 energy levels, equals 4 I should have 16 energy levels, and so on and so forth. So, for a given value of n, I have one energy, and corresponding to that energy I have n square number of eigenfunctions for hydrogen atom. What are these eigenfunctions? What are their functional forms? That we still do not know, and this is what we would discuss in our next class. In today's class, we would conclude here by discussing the hydrogen atom's energy levels, the hydrogen atom's emission spectrum, and we will continue our discussion on the eigenfunctions of hydrogen atom in our next class. Thank you for your attention.